So now I'm going to present about minor losses in pipe. So my group, it consists of me, Arif Imran bin Ikhwan Surazi, Naveen Raj and Muhammad Fazli Fitri. Okay, so I'm going to talk about the abstract. The abstract of the experiment is the flow of a fluid in a closed conduit. Such flow of crude oil in the underground pipe and flow of daily use of water is very important in our daily operation. The component is included in the pipe themselves. To connect the pipe to another, we use valve or any other connector with our desired fitting and angle to make our desired system. The pump or turbines give energy to our system to make our flow system faster. There are three characteristics of pipe flow, which are laminar, transition or turbulent flow. We also need to calculate the minor losses that happen when fluid pass through various pipe components in this experiment.
Assalamualaikum warahmatullahi wabarakatuh. So in this experiment, I will explain more about the minor losses in pipe. So the first one, introduction. The energy losses in pipe flow are the result of the friction between the fluid and the pipe wall and the internal friction between the fluid particle. Minor losses or head losses occur at any location in the pipe system where streamlines are not straight, such as at the pipe junction, bend, valve, contraction, expansion, and reservoir inlet and outlet. In this experiment, minor head losses through a pipe section that has several bends, transition, and fitting will be measured. So, what the objective of this experiment? So, the objective of this experiment is to determine the loss of coefficient KL value and minor head loss HLM in pipe component or fitting for different water flow rate, pipe diameter, and pipe bends. So the next slide is a theory. The theory of this experiment are the flow in piping system at different flow rate may be required to pass through a variety of fitting, bends, or the abrupt change in area. Additional head losses called as minor head losses HLM are encountered primarily as a result of the flow separation. By simplifying the Bernoulli equation between 2 points for the horizontal Z1 equal to Z2 pipe, the pressure loss and the total head loss could be determined. So, the equation that involved in this experiment are... So, I will explain more about the symbol on the next slide. So, the next slide are P1 minus P2 equal to pressure drop between 2 points in Pascal, rho equal to density of flowing medium kg per meter cube, G equal to gravity constant 9.81 meter per second square. V1 minus V2 equal to change of velocity of the flowing medium from point 1 to point 2 in meter per second. HLT equal to total head loss in meter. HL equal to measured head loss in meter. F equal to coefficient of the pipe friction dimensionless. L equal to length of the pipe meter. Di equal to internal diameter of the pipe in meter. V for HL equal to speed of flowing medium for the test pipe in meter per second. HLM equal to minor head loss in meter. V for HLM, speed of flowing medium in vicinity where the minor loss occur in meter per second. KL equal to loss coefficient is associated with HLM, dimensionless. H1 minus H2 equal to differential height in manometer between point 1 and point 2 in meter. So basically, the value of the KL is strongly dependent of the geometry of the component considered as well as the fluid properties, include the RE, and the mechanical function of them can be expressed. In the next slide, KL equal to phi geometry RE. In many practical applications, the RE is large enough so that the flow through the component is dominated by the inertia effect, leaving the viscous effect as secondary importance in the flow which dominated by the inertia effect. It is usually found that pressure drop and the head losses correlate directly with the dynamic pressure. Therefore, the friction factor F for very large RE in fully developed pipe flow is independent for the RE. The same condition is found to be true for the flow-through pipe component of fitting. Thus, in the most practical case, the KL for the component are function of the geometry only. In this experiment, the KL value and SLM in pipe for the different water flow rate, pipe diameter, and pipe band will be determined. So, for the Sadek expression or enlargement, KL for the Sadek expression and enlargement and contraction in circular duct or pipe are shown in figure 2. Note that loss of pipe for a Sadek expression or enlargement are based on the speed of flowing medium at the region 1, 1 over 2 V 2 over 1, whereas for the Sadek contraction are based on the speed of flowing medium at the region 2, 1 over 2 V2 2 over 2. Move on to the next slide. Figure 2 shown that the loss coefficient for flow through sudden area change. The value of KL for the fluid flow through a sudden expansion or enlargement and contraction can be obtained by considering the continuity in equation 7, momentum in equation 8, energy equation between point 1 and point 2 in equation 1 for the flow control volume shown in the figure 2. The equations that involve are A1 V1 equal to A2 V2 in equation 7. A1 V1 equal to A2 V2 equal to rho A1 V2 bracket V2 minus V1 in equation 8. Those equations can be rearranged to give the theoretical KL for sudden expansion or enlargement as KL equal to bracket 1 minus A1 over A2 bracket square equation in equation 9, whereas the theoretical KL for the sudden rotation can be expressed as KL equal to bracket 1 minus A2 over A1 bracket square in equation 10. So basically, I will explain more about the symbol. P1 equal to pressure at the small cross-section of the upstream in Pascal. V1 equal to velocity at the small cross-section of the upstream in meter per second. A1 equal to cross-sectional area for the upstream calculated using the internal diameter of the pipe, meter square. P2 equal to pressure at a small cross-section for downstream in Pascal. V2 equal to velocity at the small cross-section of the downstream in meter per second. A2 equal to cross-sectional area for the downstream calculated using the internal diameter of the pipe, meter square. And the last one is gamma equal to specific of the flowing medium, gamma equal to rho g in Newton per meter cube. So the elbow pipe bends and pipe branches, the value of the SLM and KL of the flow involving pipe component of fitting, such as elbow pipe bends and pipe branches, could be determined by experiment by using equation 3 to equation 5. An example of the typical value of the KL for the pipe component of fitting are shown in figure 3. So basically in the figure 3, there are 4 types of the component for the KL value. So the first one is elbow. The second one is 180 rated bend. The third one is T. And the last one is the valve. So that's all for me. So I will pass to my friend. Thank you.
Good evening. Now I'm going to explain the experimental procedure. First, the direction of water inflow and outflow for the tested pipe section was determined. This is in order to make sure that the water don't flow into the wrong pipe. If you want to test for the white pipe, we have to make sure that the T pipe and other pipes are closed so that the water will flow in the correct pipe. Secondly, the inlet valve of the tested pipe section was fully open and the inlet valve for the non-tested pipe was closed. The pump was turned on and the outlet valve was slowly opened until the maximum and the water bubbles in the tested pipe section was removed. The water in the tested pipe, the water bubbles in the tested pipe should be removed in order to get the correct height. The inlet flowing pressure H1 and the outlet flowing pressure H2 was for the tested pipe section was determined and the manometer tubes from those H1 and H2 of the tested pipe section of two tube manometer was connected. H1 is basically on the left hand side and H2 is basically on the right hand side. The values of H1 and H2 at two tube manometer was recorded. The actual water flow rate was determined by recording the time taken to collect the 3 liters volume of water at the tank. The opening of outlet valve was reduced and step 4 to step 5 were repeated for 5 different values of QL. After finishing, the manometer tube was removed first to avoid water bubbles in the tube. Step 1 to step 7 was for the other tested pipe section was repeated until the pump in the running condition. After finishing, all the manometer tubes from the system was removed and the inlet and outlet were fully closed and the pump and the main switch was turned off. Okay, now we're going to see the result. When we change the pressure, the H value will be different. The difference between H, which is delta H, can be calculated by subtracting H1 from H2 or H2 from H1. Either way is just the same. For sudden enlargement, the Q is calculated by changing the time into minutes, and the time in minute is divided with the volume to find the Q, which is volume flow rate. For sudden contraction is just the same. Then after these two experiments, we go to the Y type and T type. All the calculation will be same. H varies with the pressure. So does the time. To calculate the Q, we divide volume with time in minute. Same goes to the 90-degree angle band and 90-degree angle and 90-degree band and 45-degree angle. In order to get the most accurate value of Q, we can find the average value by calculating the total amount of Q dividing with the total number of Q. Okay, now I'm going to explain the discussion. Our first discussion will be calculate the minor head loss and the loss coefficient for each of the pipe component of fitting. The Q average is found previously, and all these four values, the diameter and thickness, are already given. We calculate the inner diameter using this formula, and it is used to find the inner area of the first pipe, which is 0.000227 meters, and diameter of the second pipe is found using the same formula, and the area of the second pipe is found using the same formula as well. In the second step, we have to find the KL, and the third step, we have to find the V, which is the velocity, in order to find the minor head loss. KL is found using this formula, and our KL is 0.4118, and velocity is found using this formula, which is 1.71 meter per second. Minor head loss is found using this particular formula, which is 0.06137 meters. For sudden contraction, it is just the same. The Q average is found previously, and the diameter and thickness value is given. We are using the same steps to find the diameter and the area. Step 2 and step 3 are repeated again. We can see that the final value is just the same, no matter it's going one way or the other way, which is going on sudden contraction or sudden enlargement. The value of head loss for the same particular type of diameter is just the same. For 90-degree angle, K value, which is coefficient of loss, is already given, which is 1.5. It is taken from the table. For step 1, we have to find the velocity. Since the KL is already given, which is found from the table, we don't really need to find KL. So our step 2, which is our final step, will be finding the minor loss, which is 0.1923. As we see in the previously, for both sudden contraction and sudden extension, the final value, which is head loss, was same. Same goes to 90-degree bend. So the KL value for both situation is just the same. We can see that the velocity is same as well as the head loss. In 45-degree angle, the value of KL is different because of the angle itself. Due to the difference in KL, the value of KL didn't affect the V, because in the formula of finding the V, we don't include the KL. So the V for both 90-degree angle, 90-degree bend, and 45-degree angle is just the same. Only the head loss is different due to the presence of KL in the formula, which is 0.05182 meter. For Y type, the KL for both situation for KL for Y type and T type is just the same, but the Q is different. For Q average for Y type is 0.00312 meters and T type is 0.000382 meter cube per second. You can see that the diameter are just the same. In step 1, we have to find the V. The V value is different due to the Q values. Since the Q values are different for both situations, so the V value is different. For the value for minor loss is different as well due to the presence of V. In our second discussion, discuss the effect of the different water flow rate, pipe diameter, and the pipe bend on the value of loss of coefficient. Loss in coefficient depends on diameter of pipe. The bigger the diameter, the less friction it will contain and less energy will be lost. Thus, the lower the loss coefficient. Our second reason will be pipe bends. The longer the bending of the pipe, the lower the loss of coefficient. Our third reason will be flow rate. If the flow rate is low, the friction loss in the pipe will be lower, thus the lower the loss coefficient. Our last discussion will be briefly discuss the factor distributing to the error of inaccuracy in the experimental data and propose recommendation to improve the result. Due to the presence of errors, the data collected is inaccurate. One of the factors that contribute the error in the measuring is the measuring instrument that we use consists of zero error. We must ensure that the instruments are in good condition before conducting the experiment. Another way of avoiding this error is by subtracting the initial reading in order to get the accurate value for the final reading. Moreover, the eye of the observer are not at the same level while taking the reading on the manometer. Data should be taken repeatedly and find the average. In this way, the data's accuracy will be increased. Furthermore, the presence of air bubble in the tube that cause the height value to be inappropriate. Before or during the experiment, make sure that there's no air bubble in the tube, especially while taking the reading on the manometer. Bubble should be eliminated. As I told previously, air bubble will affect the height of the pressure. Finally, all water flow must be turned off before changing the pipe to make sure the water level does not exceed the maximum value in the tube. That's all from me. Thank you.
So now, lastly, I'm going to talk about conclusion. In conclusion, the objective of the experiment are achieved as we can prove that the loss of coefficient KL and head loss of different type of pipe have huge relationship between the diameter of the pipe, water flow rate, and pipe bends, and both of the value can be calculated using different equation. Since the pipes have nearly same value of either water flow rate, the diameter of the pipe, or pipe bend, then the coefficient and head loss value obtained can be close to each other despite they have huge differences in head loss in coefficient. As comparison between the value of coefficient for several pipe, Y type and T type stand the highest, which is 2.0, while the lowest is 45-degree angle, which is 0.4. While for sudden contraction and expansion, 90-degree bend and 90-degree angle are at 0.4118, 0.7 and 1.5 respectively. Whereas for the head loss for a different type of pipe, the arrangement is in ascending order is 45-degree angle, sudden contraction and expansion, 90-degree bend, 90-degree angle, Y type and T type with the value of 0.051 0.5182 meter, 0.06137 meter, 0.06502 meter, 0.1923 meter, 0.1927 meter, 0.2887 meter respectively. For the T-type pipe, it recorded the highest head loss. It's mainly because the pipe bends are very short, causing the water flow rate to be high at the value and the coefficient value. While for the value of head loss of Y type and 90-degree angle is almost the same because the water flow or the flow in both pipe is nearly the same despite they have difference in coefficient value.